Dear colleagues, welcome back to the IFS Seminar, and this time it is my pleasure to announce our speaker, Gandalf Lechner, from the University of Erlangen's Institute for, how it is called?
It's just the math department.
Yeah, the math department, let's call it that way. Gandalf has been working in mathematically rigorous quantum field theory for quite a while, and he has many influential contributions to the field. And today he'll hopefully teach us a little bit about the notion of integrability in the context of algebraic quantum field theory and its relation to other kind of perspectives on integrability. So integrable quantum field theories, inverse scattering, local von Neumann algebras, asymptotic completeness. Please, Gandalf, and then you can decide whether the audience should interrupt you for questions or whether they should wait for you to announce pauses for questions. So that's up to you. So please go ahead.
So first of all, thank you very much, CI, and the whole community behind this. I'm not entirely sure where I am virtually. Well, I'm physically here in Erlangen, but I might be in Belgium, I suppose, yeah? Anyways, thanks a lot for giving me the opportunity to talk. And to answer your first question, yes, please do ask questions all the time. I think it's much better than saving them for the end. I'm not sure if I will see the chat. So if you could alert me of anything that might come up on the chat, then I can also address that.
Sure.
Yeah, topic is, as you said, integrable quantum field theories. I'm not sure about everybody's background here, but I heard it is mixed. So I want to start light and not go too much into the scary bit with von Neumann algebras and so, because I have the feeling maybe not too many operator algebra people are here, but rather to convey the main message and the idea of this construction. Okay, so let me jump into that with an overview. So now I see on my iPad the second slide, but on this screen the first. So you probably don't see the second, right? Maybe I need to leave the presentation mode. Okay, so now you do see that, right?
We do see it, right?
If I go to presentation mode, yeah, okay, let's try. If something is stuck, please let me know. Okay, topic of today's talk is a program for mathematically rigorous construction of certain quantum field theories, so certain examples, models of quantum field theories. And maybe I should say a very few things about quantum field theory in general. So because maybe that's not everybody's subject here, but you might all know that quantum field theory is a very successful theory in the sense that it's the basis of our current understanding of elementary particle physics, really. Sometimes has led to extremely precise matches between theory and experiment, and is also some motor and inspiration for research in mathematics and in various fields of mathematics. There are, however, also problems with quantum field theory. It's not only a success story, namely the construction of examples, and I will come to what an example really means in more detail later, is always extremely difficult unless you talk about particles that don't interact at all. So it's usually a challenge, and many interesting models like the standard model are not known to exist in any rigorous mathematical fashion. Oftentimes, this is a problem that can be seen as a convergence problem. You do some kind of expansion in a coupling constants, which somehow measures the strength of the interaction. And you want to do a kind of Taylor expansion, and one knows that such an expansion will always diverge. You know, there's no chance it can converge. Somehow, miraculously, if you do the first couple orders, you can't do many orders anyways because it's so complex. You get sometimes very nice matches with experiment, but there's no proper understanding of the full construction of many models. This might be emphasized also very well with the Millennium problem. So on the list of these Millennium problems that you certainly heard of is the Young-Mills and mass gap problem, which asks you to construct a specific quantum field, the Young-Mills theory, and show that it has a mass gap. So just to highlight, there are challenging problems out there in this field. That's not what I wanted. Yeah. So in this talk, I don't want to talk about quantum field theory in general, but I want to talk about the construction of some, say, fairly modest model theories. Modest in the sense that they are integrable. I will come to what that means in this context, but you can, as a rough idea, you can think about it as it's a kind of weak interaction. Yeah? So for instance, you would have scattering processes in which there's no particle production. Typically in relativistic setup, you do have particle production at high enough energy. And I want to give you an overview of some non-perturbative construction problems for specific quantum field theory models. And we will use, at least in the second part of this talk, an operator-algebraic setting, which connects us to what is known as algebraic quantum field theory, but I don't assume any background on your side in algebraic quantum field theory. Okay. So here you can see I start out really basic. Yeah? So we are on two-dimensional Minkowski space. Basically the simplest space-time you can imagine. There's one time direction. Time for me will always go up in such pictures, and one space direction. Yeah? At first, we look at configuration space. So let's recall a few things from special relativity. So here you see the forward and backward light counts. Yeah, so that divides Minkowski space into space-like vectors and time-like vectors and light-like vectors. Yeah, so these are things you've certainly seen before. And it also gives us an opportunity to talk about the relativistic symmetry of the space-time. Yeah? So the symmetry of Minkowski space is that of the Poincare group. The Poincare group is generated by a couple of one-parameter groups. In particular, there are the translations. So that's actually a two-parameter group because you can translate in time and space. Yeah? So simply translations on the plane. And their generators would correspond to Hamiltonian and momentum operators. So these are of physical significance. Then there are the Lorentz boosts. So these are like relativistic rotations, if you like. So the Lorentz boosts have the light rays as their eigenvectors, and then the orbits, they look as indicated here. Yeah? So that's a one-parameter group of Lorentz boosts. And my notation will always be that I use lambda t as this 2x2 matrix here with these orbits as indicated. Yeah? So that's a Lorentz boost matrix with rapidity t. So the physical significance of this parameter t is that of the rapidity. Okay. And finally, there is a reflection in the Poincare group, namely the space-time reflection. So it maps such a two-dimensional vector x into minus x. So it flips both the time and the space coordinate. All right. That tells us something about, say, the space-time. Very often, we also work in a dual picture. Now I think it's stuck again, isn't it? Okay, so I will try like that. Unfortunately, that means I can't really write, but you see my cursor? Mm-hmm. Okay, so we will have to do with that, I'm afraid. Let me go here to gallery view. Okay. Okay, so I was saying we will oftentimes also look at the dual picture, namely energy momentum, so dual in the sense of Fourier transforms. And here two-dimensional Minkowski space becomes a two-dimensional energy momentum plane. And in this picture, well, I now want to indicate what the energy momentum spectrum of a typical quantum field theory would look like. Yeah, we will certainly have an eigenvalue for both energy, eigenvalue 0, and momentum, momentum 0 that corresponds to the vacuum state, which should be empty in a sense and of 0 energy and momentum. We would also expect that if our theory describes massive particles of mass m, say rest mass m, to have such a hyperbola in our energy momentum spectrum, because that exactly corresponds to the energies a moving particle of mass m would have. So it would have rest mass m, and then the other configurations are given by Lorentz boosting the rest position. So this black line here would correspond to the energy momentum of single particle states. In a field theory, of course, you are not just bound to vacuum and single particle states, but you have 2 and 3 and n particle states. So there's much more to the energy momentum spectrum. And starting from a mass of 2n here, you would have a continuum of all points above this hyperbola, a continuum in the energy momentum spectrum. So that's the kind of energy momentum spectrum you would expect in a quantum field theory describing a single species of massive stable particles of mass. Okay, let's switch to a more mathematical setting. So what does this mean now on the side of mathematical input? First, let me formulate our one particle space, one particle Hilbert space. So I take here this L2 space on the real line with Lebesgue measure. That corresponds exactly to particles having energy momentum spectrum on this hyperbola. So that's a natural representation space for an irreducible representation of the Poincare group. And since we want to allow inner degrees of freedom, like where a gauge group could act, I will take a tensor product with some other Hilbert space K, which we will always take to be finite dimensional, although there are also infinite dimensional examples. And this tensor product here with K, so K could be trivial. It could be just complex numbers. In that case, we would speak about scalar models, but it could be n-dimensional for an O and sigma model, for instance. Okay, so on that space, we have a unitary positive energy representation, which I would call U of the Poincare group. And let me explain my notation here in these formulas. So psi is a vector in this tensor product space. Theta, well, of course, means evaluating here this rapidity argument, and this index alpha, it corresponds to some chosen orthonormal basis in this internal degree of freedom space K. So does that make sense, that notation to you, I hope? Good. So then how does the Poincare transformation of translation by x and boost by rapidity lambda act? Well, simply in this way, translations act multiplicatively in momentum space, and the boost is just a shift in rapidities. So that represents the connected part of the Poincare group. And the space-time reflection would be implemented by conjugating all the outputs of that function and also introducing a bijection on K, which I introduce here by conjugating the index. So that's like the anti-particle. So that gives you a proper description of the one particle space. N particle states should then be described by certain vectors in the n-fold tensor power, and we want to take into account statistics, so it should be some kind of suitably symmetrized subspace, for instance, totally symmetric or totally antisymmetric if you have elements. The full Hilbert space is then direct sum in all particle numbers, so you would have something like a Fock space. I will be more precise about that in a minute. It won't be in our constructions, it won't be a true Fock space, but something slightly twisted. In particular, we will have a zero particle state, namely this spectrum vector, which I always call omega. Okay, now let's talk about integrable scattering. So typically in quantum field theory, scattering is a very complicated process. And you can't even talk about a certain state of your quantum field theory having a particle interpretation at all, or particle interpretation of a definite number of particles And you will have production processes, so two particles collide and thousands might come out. Yeah, so it's a very complicated process. However, in some scenarios, there exist examples where you have simple scattering. And that's exactly the setting of an integrable quantum field theory. Yeah, so in that case, you have infinitely many conservation laws that severely constrain the dynamics. So you have so many conservation laws that, for example, there's no particle production. So the conservation laws you can think of as prototypical examples are, well, energy and momentum, obviously, but then also powers of energy and momentum. Yeah, so like that not only the sum of all momenta is conserved, but also the sum of squares and the sum of cubes and so on. And that very much restricts the dynamics. One common feature of these integrable field theories is that the set of all incoming momenta equals the set of all outgoing momenta in any n-particle scattering process. So that means there is no momentum transfer. There are still effects like time delay, for instance, or there could be a non-trivial interaction in internal degrees of freedom. So there's certainly still energy-dependent scattering going on, but in some sense, it's a little closer to what you might know from quantum mechanics, scattering at a transparent potential. And examples of such theories which have this behavior are, for example, the Sine-Gordon model or the Turing model or the Ising model or O and sigma models and many others. They only exist in 2 dimensions. And one feature that we will also use later is that n-particle scattering can be described as a successive scattering of 2 particles each. So the n-particle S matrix will factorize into a product of many 2-particle S matrices. That's called a factorizing S matrix. Yeah. Okay, that gives you a rough impression of what integrable scattering looks like. One can certainly say that for such quantum field theories, the 2-particle S matrix is the defining quantity, really. Yeah? So it is an object that should, in principle, describe all properties of the theory.
Is it, sorry to interrupt, is it some effective Gaussianity assumption that you're putting into that?
This assumption, Gaussianity, I would not be sure how to phrase that, but it can certainly be phrased in very different languages. I mean, so far I also did not really mention how I want to model quantum fields. Yeah? So it could be in a Euclidean setting, or maybe in a path integral setting, or in an operator algebra setting, and how integrability will look like, it depends a lot on that. Yeah? I will give you a clear-cut description of such integrability in an operator algebraic setting later. But Gaussianity, I mean, to me, that sounds like a description of some specific state, right?
No, it's true. It's just when you say that the S matrix is kind of described by two-point, interaction. That's.
I see. Yeah, so there is certainly some resemblance of a Gaussian state where an endpoint function factorizes into a 2-point function, but it's of a different nature here, really. Yeah? Okay. So in such an integrable theory, you would have still all kinds of states, Gaussian or not. Yeah. So for instance, you would have 1-particle states, which are certainly not Gaussian. Yeah. Or you might have a vacuum which could have this property, but it's really something of a different nature, I would say. It doesn't single out any state so far. It should describe all scattering states. Yeah, does that answer your question more or less?
Yes, yes.
All right. Then let me move on with some pictures. So on my screen, this is reasonably small. I hope it's visible on yours. What I'm working towards now is a definition. Yeah? It's a definition of what I want to call rigorously a 2-particle S matrix, and I give some motivating thoughts how that should look like. And what I want to draw here are 2 world lines of particles, stable particles that cross in one point. Yeah? And they should be labeled, well, first of all, by rapidity. So this comes at rapidity, say speed, θ1, which shouldn't change throughout the scattering process. And same for this, should have rapidity theta 2, should not change. But these half legs of this diagram are also labeled by indices alpha, beta, corresponding to the basis of your internal degrees of freedom Hilbert space. And they might change in a scattering process. So we view this as a comic of a two-particle scattering process, and we somehow want to associate a certain amplitude with it. Yeah? So a scattering amplitude. Yeah, that should depend on all these data. It should better only depend on the difference of rapidities by relativistic invariance, because the boost translates in rapidity. Okay, so such objects will come up a lot. And what is also very relevant, if we talk about factorizing scattering, let's look at a process where three particles scatter. Yeah, so just drawing three lines that intersect in 3 points. And you can then argue it should not matter if I take this middle line here and move it from the left over to the right. Yeah? Which would, however, change the intersection points quite a bit, and would, if this is to be read as a product of three S matrices, it is an equality for products of three terms on both sides, which a priori are different. Yeah? So this is a kind of consistency equation which tells you that a three-particle process can be meaningfully factorized into a number of two-particle processes. Okay, with that motivation, let me now give a true definition about what I will call a two-particle S matrix. The setting is that of this single-particle Hilbert space described before, and the representation of the Poincare group will be fixed. Then definition is a two-particle S matrix is a continuous function, so it depends on the rapidity. Yeah? So that's why I call it like that. From the real line into operators on 2 copies of K, yeah? So because it's about two-particle scattering, such that first of all, S of theta is a unitary for all arguments, but that is simply conservation of probabilities. And second, it solves this factorization or Young-Baxter equation that I alluded to on the previous slide. Yeah, so if you draw this diagram with the 3 lines and you convert into formulas, that's what you find. Yeah? This kind of equation here. I'm not sure if, so is Young-Baxter equation well known in the audience here, or is it not? It is, good. It's a complicated equation. It's difficult to solve. Some solutions are known, but certainly no overview over all solutions. And then there are more properties that one would like to put into this definition. The third one is maybe surprising at first, because it talks about extending this function to complex rapidities, hence complex momenta. But you can view it as a consequence of, say, causality. Yeah? So if you have an ordering between cause and effect, that's like a support restriction in position space and should correspond to analytic properties in momentum space. Yeah? So S matrices always have analytic properties in momentum space. And the right one to consider here is that this function S extends to a bounded, matrix-valued, an analytic function on the complex strip where the rapidity, imaginary part of rapidity, is between 0 and pi. So that corresponds to the physical sheet exactly. It's half the complex mass shell sheet. And I don't want to give the full definition because there are various additional properties. So crossing symmetry is a property that tells you how the boundary values of this function at the real line and real line plus I pi are related and more, you know, TCP symmetry and whatnot. But you should take from this, there is a clear-cut definition. Yeah? And there are examples too. So for example, if you talk about scalar models and you just have trivial internal space, this function will do it. Or if your internal space is C to the n, then there is an expression of that sort where P, 1, and F are specific constant matrices, and the sigmas are specific combinations of gamma functions, and that would be believed to correspond to the sigma model. Yeah? And so there's a list of examples. Our task now is, given any such S, any such two-particle S matrix S, come up with the construction of a quantum field theory which has this S as its two-particle S matrix. Yeah. That's what one would consider solving the inverse scattering problem in this context. Right. Briefly, a quick slide on quantum field theory in general. So because I didn't say very much about quantum field theory yet, I said a few things about Minkowski space and energy momentum and so on, but not about quantum fields yet. So usually a quantum field theory is described in terms of quantum fields, right? Phi of x, let's say, which roughly, so dropping many mathematical details, roughly you think of phi of x as an operator, a field operator on your physical Hilbert space, which is somehow localized at the point x. It should transform covariantly under your representation of the Poincare group. It should be local, namely if you evaluate it at points x, y that are space-like to each other, then you should have no uncertainty relations, yeah, should commute. And it would usually be described in terms of an interaction Lagrangian, which is then given some perturbative meaning by renormalization. So that would be the usual approach. And once you have such a quantum field theories and they satisfy the right properties, you can in principle determine the scattering behavior. So you can compute what happens in collision processes and compute the S matrix governing that. Right. In the integrable situation, however, it makes maybe more sense to take an inverse scattering point of view, namely not to define your field theory in terms of a Lagrangian, but rather in terms of the S matrix. That should be the defining quantity after all. Yeah? Yeah, so fix an S from the previous definition and then construct a quantum field theory, maybe such a field phi or in some other language.
Question. So can we say that in some sense you are reconstructing the theory based on knowing its solutions?
No, I would not say that, because a solution to me would mean you have, for instance, the endpoint functions or the net of Neumann algebras or something like that. So if I give you such an S matrix, it's not even known if there is a quantum field theory that has this S matrix. So when I say, maybe on the previous slide, I said there are examples. For instance, there are the O and sigma models. The O and sigma models are not known to exist. Yeah, so this is perturbative evidence, yeah, let's say. Yeah? Or some are known to exist. Well, I'll come to that later. Yeah? So, but most of there is not a very tight mathematically rigorous connection between the two. It's certainly not saying we take a solution and then somehow rephrase things. Yeah? So there will be S matrices that don't have a corresponding quantum field theory.
Yeah, but with the two-particle S matrix, you also assume that there is a factorization. So in principle, you can compute the endpoint functions, right?
You cannot compute endpoint functions. No, and maybe that is worth pointing out here in this formula. Mm-hmm. So people try oftentimes to construct endpoint functions, and maybe that's what you had in mind, yeah, with ideas from the form factor program, like here, one-point function or endpoint function. And you could write these as certain series of integrals or form factors. Huh? But you don't know if that exists. Yeah? So it could easily diverge. Yeah? So there are no proofs of that sort. Yeah? So we are really worried, say, with existence and uniqueness, maybe existence most of all. Given such a S matrix, is there really a quantum field theory out there with that scattering behavior, or maybe not? And if it is, can we say anything about it? Yeah, so I will construct a field theory, and in the end, we must ask ourselves, does the S that goes into the definition, does it really describe scattering? That is also not clear from the beginning. Yeah? It will enter as a sort of parameter.
Mm-hmm. So basically, you're saying that you have only the two-point S matrix, and that is not enough to have any full solution of the theory. You don't even know if the theory exists, but you can, in some cases, you can use just this information to construct the theory.
That's right. Yeah. So, and it will be solely based on the two-particle S matrix. Yeah? In the end, I will verify that the scattering behavior is indeed the expected one, and factorizability will be a result. Yeah? So the input is only the two-particle S matrix.
But by two-particle S matrix, you mean 2 to 2 scattering, right?
Yes. Yes. 2 to 2, because particle number should be preserved, so it's 2 to 2 exactly. Okay, so this is usually taken up, as I mentioned, in the form factor program. Since I'm not on my iPad here, unfortunately, the citations that I wrote in by hand are missing here, but there are many people who worked on that. I mean, wow, Smirnov comes to mind, Babujian, Fring, Olaja, Cavaredo, Karowski, lots of people worked on that. Yeah. And there are many results, and these are extremely complex functions to compute. Typically, one does not get to formulas for endpoint functions or convergence results, however. So hence the focus of this talk will be an alternative approach, and that's what I want to talk about. Okay, now let me go into a somewhat more specific construction. And please, if there are questions, interrupt me anytime. I don't need to cover everything. So I'm on slide 7, but I should go slow now because I will now really explain the construction. So initially, I mentioned what our one-particle space looks like. It was this L2 space tendered with an internal space K. And I said our full Hilbert space should be a kind of Fock space over that. Yeah? That I would now like to make more precise. Yeah, so first of all, take any such S matrix from that definition. So I mean a 2 particle S matrix satisfying all these properties, and define an operator capital or boldface S. Yeah? Boldface S is very similar to S. It acts on tensor square of H1, and what it does is it multiplies with this function S, and here it flips the arguments. Yeah? That's the definition. It's some unitary operator. And what you can also check is this S generates representation of the symmetric groups. Yeah, so in particular, this capital S, if you apply twice, you're back to the identity. That's because of some property of the S matrix that I didn't spell out. So you can use it to generate representations of the symmetric groups. Namely, if you have a transposition that exchanges K and K plus 1, nearest neighbors, you would just act with this S on the tensor factors K and K plus 1. Yeah? And then you can go ahead and check if this really defines the representation of the symmetric group on the n-fold tensor power of the one particle space. Right? And then the definition of what's called the S-symmetric Fock space is, well, let's look at this formula first with these projections P. They are just given by averaging the representation. Yeah, so you just sum up all group elements in the representation and divide by the order. That's a projection onto the subspace on which the representation acts trivially. Yeah? And then you sum up all these subspaces. So that's the definition of the S-symmetric Fock space. If your S matrix is simply the flip, this is nothing but the Bose-Fock space. If it's negative flip, it's nothing but the Fermi-Fock space. In general, it's some different form of symmetrization. This, in the end, is not terribly important. It's a convenient choice of space on which we work on. We could choose another one, but this is convenient. So from Bose and Fermi-Fock space, you are used to annihilation and creation operators. Yeah. Also on this S-symmetric Fock space, you have annihilation and creation operators. And this is what I write down here. And I see a little typo here. So I wrote on the space, you have creation and annihilation operators depending on S, of course, and the one particle vector psi. So this psi is xi, sorry. And how does the creation operator act? Well, it tensor multiplies with the corresponding one particle state and symmetrizes. since Ricardo is here, I should say left tensor multiplies. It could also right tensor multiply. That would be a different kind of thing, and it will come up later. And the annihilation operator, simply the adjoint of that, it reduces particle number by one. Okay, I should get going. So that is not much. It's the asymmetric Fock space, including an algebra of creation and annihilation operators. They satisfy the commutation relation of the Zamolodchikov-Faddeev algebra, I should say. Now, inverse scattering construction 2. Let's look at some explicit quantum field operators, which look very simple by quantum field theory standards. Yeah? So I'm not writing the rigorous form, but just the distributional kernels, but it can be given very rigorously. Yeah? So simply the idea is you take a creation operator paired with such a plane wave, annihilation operator with the opposite, and integrate. It looks almost like a free field. Yeah? If S is a flip, it's exactly the free Klein-Gordon field. Yeah? These operators can be given proper meaning as essentially self-adjoint operators on this asymmetric Fock space. So I don't want to go into that, but there are nothing fishy is hiding there. It's certainly non-perturbative. It's not much more complicated as a free field, really. Yeah? You don't need any perturbative expansions. But you can then wonder, well, they somehow depend on S, and what are their properties? I mentioned already, in case you take S to be simply the tensor flip, yeah, just a transposition of a tensor product, then this is nothing but the free Klein-Gordon field. So it's certainly not terribly interesting. What you do have in general, well, first of all, is covariance. And we take that field and act on it with your Poincare representation with a translation and a boost. And you see, you can check it behaves perfectly covariantly. So as you would expect, as it should. For translations and boosts, but not for TCP. So if you act with a TCP on it, this is not true, what I wrote here. Yeah, so this would be the expected behavior of an honest quantum field, but this is broken here. And it is also not something simple. Yeah, it's just not that. Yeah? And locality, so you would expect these fields should commute a space-like separation, but this is true only if you look at the boring free field. In all other cases, it's just wrong. Yeah? So maybe your first conclusion would be this is not good for much, yeah? This field. Yeah? So why should we bother? However, there is a hidden locality property in it, and that is crucial for what follows. Yeah? And to see that, you should look not at one field, but at two. You should look also at the TCP transform and call it a second field phi prime, yeah? Which is simply the TCP transform of the old field. And then there's a little theorem which tells you the field and its partner field phi prime, they do commute, well, if X is space-like to Y and left space-like, which is more specific than just space-like. Yeah? I will come to that. Yeah? So there is some kind of locality still hidden in here. And to prove that, you do need these analytic properties of the S matrix. They are crucial in that. Yeah, so let me not go into the math details, but rather explain what left space-like means. Yeah? So there is a certain duality between left and right going on, but in a relativistic setting. Yeah? So a relativistic half space you would consider to be this wedge. So just look at this picture here, this green area extending all the way to infinity to the right is what's called the right wedge. And it's called a complement, so all points space-like to it is simply the left wedge. Yeah? So these are like left and right in a relativistic setting. And then let's look at this picture where you have two wedges that are space-like in this way. Then this commutation result can be phrased by saying phi of x and phi prime of y commute if these two wedge regions don't overlap and are space-like separate. So it does make a difference if you swap left and right. Yeah, so then these wedges would overlap heavily and you would not have commutation. So the interpretation is that this field phi of x is not localized at a point in space-time, but rather in this infinitely extended region, well, it's not really just a gauge string, but it's a wedge attached to this point. So it's has only weak localization properties, this basic field coming from the S matrix. Is that reasonably clear? Because it's a crucial point, I should ask. The localization properties are much weaker than what you usually have.
Maybe you could comment on whether this is somehow related to the topology of a two-dimensional space, and whether you expect it to be to reduce down to the original locality if you can go somehow to higher dimensions, because we have also such pathological things when we consider Green's functions for some PDEs in 2 dimensions. They are less local than those in higher dimensions. Are these things related, or it is the best you can expect at all?
What can I say? You do have such phenomena also in higher dimensions. There, a wedge would be defined to be exactly that thing, but translation invariant in all other directions, so even bigger, if you like. Yeah, not string-like, but large. Yeah, so with an infinite edge attached to it. Right, I might come back to it a bit later. So it goes under this phrasing of these polarization-free generators. So these wedges are very typical regions to consider in Minkowski space, just because they have the property, if you take the causal complement of the set, it looks the same. Yeah, the shape is the same. That is very different, of course, if you look at the causal complement of a point. Yeah? So then it breaks into these 2 big regions, or the complement of a ball or something like that. Yeah? So these wedges are preferred in many ways. Also, when it comes to modular theory, they are preferred. And there's a long story behind that, which I can't go fully into, I'm afraid. Yeah? But these are, in some sense, our favorite regions, although, of course, they are much larger than a physical laboratory, and we need to go to smaller regions. Yeah?
Just a trivial question. So if you didn't do this prime twist, so the standard commutator would be both left wedge, therefore they would have some overlap. That's why it wasn't 0, right?
No, if I would drop the prime here, the commutator, well, it would not be 0. It would also not be anything easy. Yeah, so this, it would have a 2-particle it would have a 2-particle creation part, a 2-particle annihilation part, and a constant part, and they would all not be 0. Yeah, it would be not. Yeah, you can't really simplify it. Yeah? So it is very crucial that there's a prime here, yeah? So that you take the partner field. Phi as such is not really doing that. Yeah? So, and you can view it as maybe that's what you mean. Yeah? So as one wedge. And you look at another wedge and they heavily overlap. Yeah? So, and that would be an explanation why you shouldn't expect that to be 0. That content. Okay, so we have this funny localization property. Now, a little bit of operator algebras. I'm not sure about anybody's background here, well, except for people I know from Erlangen, of course. The message for the construction is we do have nice fields, but with 2 weak properties, in particular regarding localization. Yeah, we want to somehow improve our localization from wedges to small sets. Yeah, ideally points, maybe that might be singular, so maybe bounded regions, yeah, or small diameter or something like that. And to do that, it's useful to use a setting that uses von Neumann algebras, because it's all about commutators. And commutators are very natural when it comes to von Neumann algebras. So let me introduce the following setting. With this curly M, depending on our S matrix S of X, I will define basically all functions of the field phi prime smeared with the test function F having support in this wedge. And then you can be very precise about it and say, I take bounded measurable functions and things like that. Certainly bounded operators. No? Exponential, for instance. No? And I will also look at the algebras given by commutants, so all operators commuting with everything. No? That's also a von Neumann algebra. For the purposes of this talk, it is not entirely, it's not too important that you know in all detail what a von Neumann algebra is, but it's some kind of algebra of operators with very nice properties. That's really all one needs to know at this level of superficiality. Okay, so this just means instead of the fields, I look at functions of fields. Okay, then you can derive a couple of properties of that. So you can check if you take this algebra and act on your vacuum vector, you can generate basically any vector in your Hilbert space. Is a property that is typical in quantum field theory, goes by the name of a Schlieder property, holds for all S matrices S. And the same is true if you do that with the commutant algebra. So that requires some work, but can be done. Yeah? And lastly, you can check that the commutant of this algebra is given exactly by the opposite field. Yeah, so it's a kind of dual situation. Yeah, so you on the one hand, you have the field phi and phi prime, and in certain configurations they commute, and they generate each other's commutant. So there's nothing in addition that commutes with both. Goes by the name of Hart duality. Okay. This brings us close to the setup of algebraic quantum field theory, where you describe a field theory not really in terms of quantum fields, but you still keep the name quantum field theory. You describe it in terms of local observables. Yeah? So the idea is you look at some space-time region O, could be a double cone, could be a wedge, could be a point or whatever. And to that you associate an algebra of operators that you interpret as the observers that you can measure within that region O. And that can be nicely phrased in terms of set of axioms. And once you are in that setting, you can study if you can go to a point-like field setting or vice versa. That's oftentimes investigated. But for instance, if you think of P-phi2 models, the Euclidean ones, when they were transferred back to Minkowski space, first it was checked that they satisfy the axioms of algebraic quantum field theory. Later on, they were also established in this endpoint function language. Anyways, that's this kind of formulation that we have. Now, the crucial idea is how to go to algebras of observers that are localized not in such a big wedge here as on the left or on the right, but as in a small region as the one in the middle. Yeah, that's called a double cone. Yeah? So this region in the middle here has a property that it consists of all points space-like to the right wedge here and the left wedge here. Yeah? So what should I take? Yeah? I cannot write down any easy field localized in there. It must be complicated just because of Heisenberg's uncertainty relation. So our answer is I simply take all possibilities. So what are all possibilities? Well, anything localized in here should at least commute with everything in here. And there I have explicit fields, and with everything in here. And there I also have explicit fields. Yeah? And this is just an operator algebraic way of writing. I take all operators that commutes with stuff on the left and stuff on the right. Yeah? The identity will do it. That is trivial. But apart from that, it is not so clear which other operators might do it. Yeah? And you can view it as a relative commutant, but given that my time is running faster than expected, I don't go into that very much.
Maybe a short question. Here we assume that if the wedges are separated, then the two operators definitely don't commute, or the other way around.
Yes, so the setup is as in this picture. These two wedges are shifted apart in such a way that they are space-like to each other. And there is some open region in the middle that is space-like to both of them.
Right.
Otherwise, this OXY is simply empty.
Yeah, what I'm saying is that the intersection might potentially contain operators spontaneously which are not contained in O, but nevertheless happen to commute somehow.
So far, well, what's the status of operators in the middle here? I don't know any non-trivial operators to start out with. I only know conditions they need to satisfy.
Right.
I only know, well, whenever I have an operator that I want to interpret as being localized here, Well, it ought to commute with the left field with
that's...
such supports and right field with such supports. And then you could think, well, it's a simple condition. I just solve it, but it's not simple. And you can't solve it.
Yeah, what if there is an operator which is not localized in O and yet happens to algebraically satisfy the commutation relation? It's somewhere else, but still commutes with those.
If it commutes, I will view it as being localized in O.
Okay.
That is by definition what it means to be localized, yeah? To be compatible with everything that is space-like to the given region. Yeah? So that is my definition of being localized in O. Yeah? Okay. But I wonder about the solution set of this definition. So the question arises, if I start out from any S matrix, are there any operators in there, or many, or can I say something more, right? So the question is really, is this algebra localized in a double cone? Is it just multiples of the identity or not? And possible strategies for answering, well, one strategy would be, well, I try to solve these commutation relations. And that is basically what you can view the form factor program as doing exactly that. And you can compute certain matrix elements and maybe to some order and particle number. But to really construct the operator, it must be extremely difficult. Now, when you have an interacting theory, even if it's integrable, a local field acting on the vacuum will create any number of particles. It must be terribly complicated. There's no way of easily writing it down. And hence here, I would like to decide the non-triviality abstractly. I would like to argue, are there solutions without specifying them in detail? Okay, so let me look into that. Let's see. There is one more slide of operator algebra business going on. Sirai, what about my time actually? I'm looking slightly worried at the clock.
Yeah, don't feel much restricted. It's not very strict. So you have, say, some 10 minutes plus a little bit.
Oh, I with 10 minutes, I hope I can do. Yeah. So this is now a technical slide. So it will talk about the question, how can I decide if there are operators here commuting with these known operators and these known operators without writing them down? Yeah? And the catchword is modular nuclearity. Yeah? So I introduce a few facts from operator algebras. So if you have such a von Neumann algebra as we do, namely there is a vector omega in the Hilbert space such that M omega is a dense space and M prime omega, so the commutant is also a dense space, then this determines certain interesting data, including a modular operator, which is a positive operator, typically unbounded, which induces automorphisms of this algebra. Yeah? So if you act on it, on your algebra like that, you leave it invariant for all real parameters. It can be viewed as some kind of intrinsic time evolution, if you like. The modular dynamics. So that goes back to the Tomita and Takesaki. So that's old stuff from mathematics, really. So we are in such a situation that we have this operator abstract. It's defined very abstractly. It is around. And the good thing is it can be computed explicitly here. Yeah, so in the case of these von Neumann algebras coming from such a factorizing S matrix, and in other cases too, you can show that these modular unitaries are nothing but the Lorentz boosts. Yeah? So in this case, two worlds meet. Yeah, there's this algebraic definition of the modular operator, which I didn't even care to write down. It's complicated and abstract, but it's there. And there's a geometric one. There's just Lorentz boosts coming from the relativistic symmetry. And here we have what's called geometric modular action. The two coincide. So that's a situation that you oftentimes have for wedges in quantum field theory. For instance, in every Whiteman theory, you have that. Okay, so that makes this more explicit. How does it help with our localization problem? Here is a theorem that combines many results from the literature. So if your S matrix is such that this map here has a certain property, so we should look at this map. What does it do? It takes an element from your wedge algebra, as it's called, yeah, so some bounded function of the fields, in the first instance, just applies it to the vacuum vector, shifts it inside this wedge a little bit by this x, and then applies this modular operator to a power a quarter, which corresponds to a boost in imaginary direction. So that one can check is a bounded map between Banach spaces. If it's even what's called nuclear, so nuclear is a bit like trace class just between Banach spaces. Yeah? So it means you can approximate well by finite rank maps in a specific way. If that is so, then this local algebra, so here this parameter x enters as the right point of this double cone, is large. So large means infinite dimensional. It means it's a type 3-1 factor. For people who know what that is, the vacuum is cyclic. It's exactly the right size for a quantum field. Yeah. And again, I have to apologize that I don't use the latest version of my slides and all the citations are missing. So this is, first of all, abstract stuff. Modular nuclearity is due to Buchholz, D'Antoni, Longo, who studied that in the 90s, I believe. It's a while ago. And then this application to these factorizing models is due to Buchholz and myself. Yeah? Just for completeness, let me mention that. So there is a certain condition on S that will guarantee you that there are many local observers. It's not a terribly easy one, but it's out there. The main message is you can try to check this condition, and it's a nuclearity condition. So you have to essentially show that some operator is trace class. So you somehow have to estimate that eigenvalues drop off quickly, or something of that sort. Yeah, that's the feeling of this property. And if you can do that, then you know local observers exist, although you haven't constructed them explicitly. Yeah? So the existence of local observers can be decided by estimates, and I call it estimates on analytic continuations and rapidity, because this delta to a quarter corresponds to analytic continuation in imaginary direction of rapidity. Yeah? So that's the main message. And then you, of course, wonder, well, can it be checked or not? Yeah. Before that, I should mention, so if this condition holds, then the construction gives you a well-defined quantum field theory. Yeah? We can then study its properties. Yeah? But if it holds, we are in a good situation. Okay, so let me give you one existence result. An S matrix, S as before, I will call regular. Remember, an S matrix was in particular defined to be a bounded analytic function on the strip imaginary part between 0 and pi. Now, for regularity, I ask, there should exist a small kappa or epsilon larger 0, such that S extends to a bounded analytic function on a slightly broader strip. Yeah, so it goes a bit down into the negative imaginary part and above pi. Yeah? So that's what I call regular. Many S matrices have this property, but not all. Theorem: if S is regular, and that's in this form is together with my PhD student Sabina Al-Azawi a couple of years back. If it's regular, 3 properties: regularity, at zero momentum transfer is the negative flip, and has a certain intertwiner property that I don't spell out in detail, but it has to do with these SN representations here. Then the modular nuclearity condition holds for X large enough, and you have a corresponding quantum field theory. Okay, so here I say something a little bit about the intertwiner property. Let me just mention it's automatic if you have a scalar model. This theorem applies to various models, for example, to the Cinch-Gordon model, to diagonal S matrices, to the Ising model. The case of these O and sigma models is, however, still open. There, the intertwiner property is tricky, and it's not known yet, although one is optimistic, but there's no proof at the moment. Right. So that basically tells you there's a bunch of S matrices that we know to lead to local, well-defined quantum field theories. We should then, to complete the circle, understand what are the properties of these field theories. Are they really integrable in some sense, and what's the scattering? So I will briefly say something about that, and then we conclude. Yeah, so far I started from a given two-particle S matrix with certain properties and constructed a corresponding quantum field theory if this modular nuclearity condition holds, which it does in many cases. That somehow depends on S. All the objects that I have depend on S. But what is the significance of that, the physical significance in these models? So what's the scattering? I mean, it could happen that I did a construction that in the end always gives you the free field theory. And that's of course not what I want. And I want to verify that this S that I built into my construction really has to do with scattering. And let me skip that and just tell you a theorem. Suppose S is of the good class, so satisfies modular nuclearity, then first of all, not looking at details, I have formulas for asymptotic states, outgoing and incoming n particle states for any number of particles n. Yeah, so I don't want to explain in detail, but there are many scattering states that I can write down explicitly and verify the corresponding asymptotic behavior. And what is, I think, the first proof whatsoever in an interacting relativistic field theory for asymptotic completeness, you have it here. Yeah? So you are here in a situation where each state has a particle number, a particle interpretation. Yeah, so a dense set of. So this is asymptotically complete. You can control all the scattering states, and you can, in particular, compute what is the S matrix, which I call here S hat because it could be different from S. And it turns out it is exactly the factorizing S matrix given from the two-particle S matrix that I put into my construction. So this basically verifies the right asymptotic behavior of the theory that I was anticipating. Yeah? So it is built in such a way that the S that it really corresponds to scattering. That's the message. Yeah. It also proves the ideas underlying the Zamolodchikov-Faddeev algebra for those who know it. So that is an exchange algebra of creation and annihilation operators, where if you exchange two creation operators, it should correspond to one particle on a line overtaking another one, and hence gaining a factor S, roughly speaking. So that is something that you can prove in this context. Okay, but I am over time and I should conclude. So let me quickly wrap up. Conclusion and outlook. So main message is that this inverse scattering problem for integrable quantum field theories can be solved rigorously and non-perturbatively using wedge local fields and modular nuclearity. This first step is perfectly under control. Yeah? So this construction works for all these S matrices I mentioned. To verify the second step, you need additional assumptions that you then need to check for the S matrix at hand, and it is checked for various S's, but not for all. And sometimes it's a question of size of the double cone. Yeah, so it could change with the double cone. Also, there are still open questions. But basically, under certain conditions on S, these models do exist and are then automatically asymptotically complete. So we have full control over all scattering behavior. We don't have control over local fields. Yeah? So I don't write down an equation of motion for a local field or a two-point function or something like that. Yeah? So that is not the kind of approach that we choose here, because we exactly want to circumvent all these problems connected with that. And well, to conclude, there are extensions in other directions, many. So again, the citations are missing. So this is not all of this is my work. So Joe Tanimoto and Daniela Karamuro worked on bound states, connection with the form factor program, Henning Bostelmann and Daniela again. And there are non-local models from non-canonical geometry. I worked with Harald Grosser on that. Free probability. So Ricardo is here. We are working in similar situation, connecting there. There are models in higher dimensions of similar nature. And Borchers, Buchholz, and Schroer considered what they call polarization-free generators that somehow characterize what it means to be integrable in this operator algebraic setting. So there's a world of literature out there. But my time is up and I should conclude here. Thank you very much.
So thank you very much, Gandalf, for the very substantial and entertaining talk. So, and we have a lot of time for questions, please.
I have a drink, you think about questions. See.
So maybe I can begin with a couple while people are
yes, sure.
Once you mentioned the characterization of integrability somewhere at, on almost the last line. So I want to raise a very naive question. So yeah, so suppose I begin with quantum field theory, say a net of observable algebras in the usual sense, which is local in some sense, wedge local, or I don't know, bounded diamonds local, or in whatever sense. And I want to ask myself, what is the criterion to check, or how do I call such a theory integrable or not, in a certain sense?
That is certainly a good question, and I will try to see if I can write something here again, because it would make life much easier if I could. Right. Let me try for a second. So could I now share my screen from the other device, or would that not be a good idea? I try. Huh? As I may not, because I'm doing, so I stop my sharing here, and I started here. And then I think it's due to weak Wi-Fi that this is not always working. But so this is something from the beginning, yeah? I just need some space to write, really. Maybe towards the end, yeah? See, there are now some names here. Okay, so characterizing integrability. So I would have two answers, I think, yeah? So one is, if you are in a situation where you can do scattering theory, yeah, so that is a kind of spectral assumption, and well, on flats, if you're in a curved spacetime, I can say less, yeah, but if it's flat and you can do scattering theory, you can in principle compute the S matrix. Yeah? For me, equivalent to integrable would mean S factorizes. Yeah? Factorizes, so that means no particle production, set of incoming momenta equals set of outgoing momenta, and n particle processes factorized into two particle processes. So that is in some sense a good answer, but in other senses not, because it's very indirect. You know? It will ask you to compute the S matrix, which typically you can never do.
And then it'll depend on a state, right? You would say this state is integrable, the other one.
No. It would not, because a quantum field theory has one and just one S matrix, yeah, governing all scattering states, and it would be a property on that one operator. But to get your hands onto it is hard typically. Yeah? So another answer is, and that is relating to these gentlemen, goes into the under the term of polarization-free generator. So what is that? Yeah? So if you take an operator A, suppose it's localized in such a wedge here, A, and you apply it to the vacuum, so A is half local, so you would expect if it's half local in position space, it should be fairly wild in energy momentum space. Yeah? So you would expect to have particle numbers, well, from 0 to infinity, yeah? in typical situations. But you could then wonder, maybe it is sometimes possible that I get only a one particle state. Yeah? To have an operator that is localized in a wedge and still creates only a one particle state, so a bit as a free field in that sense. Yeah? So that's called a polarization-free generator. And it's known to exist in any quantum field theory, always. Yeah? So that is not yet the definition of integrability or the relation to integrability. But the relation to integrability comes in when you ask it to have a certain temperate behavior. And the temperate behavior would be the following. Yeah? So you plug in a translation by X. Sorry, that was not the vacuum, of course. Yeah? So you take some vector in the right domain and you look at such a dependence, no? And you ask that this is still continuous in X and say polynomially bounded. That's what's called a temperate polarization-free generator. And in this setting, Borchers-Buchholz have shown you are very close to integrability. Yeah? So you must be in 2 dimensions, you can't have particle production. And on the other hand, in the models that I talked about, this is always true. Yeah? So this is very close to integrability. So it would be another possible answer that you have polarization-free generators, so wedge local quantities that generate only one particle states and behave in a temperate way under translations. That is also close to integrability. It's not close in any obvious way. Yeah, so I'm not saying that. Yeah, but it turns out to be like that. You have to go through scattering theory and explore the consequences of this temperateness assumption.
So does it somehow heavily hinge on harmonic analysis? Because when you have, say, a function of supported on the half line, then the Fourier transform is obviously the Hardy space of holomorphic functions on half space and so on. And if there is a direct link, then maybe one can elaborate a little bit further to see what maybe need for equivalent formulations might ensue.
This again collapsed for me, so I have to share over here. So a direct link. So what you said about Hardy spaces and so on, they do play a role here behind the scenes, which I didn't mention too much. So there are Hardy spaces corresponding to states localized in such wedges, and they go under the name of standard subspaces and so on. So they are here. They are domains for modular operators. But this temperateness assumption, it has such a feeling, right? Because it is polynomially bounded and continuous. It sounds a bit like pseudo-differential operators, yeah? But it's, I wouldn't know of a very tight and direct link, but maybe there is something, but not in the literature, I think. Yeah? So that would need some more work. There are also counterexamples when you include bound states where such temperate behavior can break down. Yeah, so Jo Tanimoto has studied, and sometimes with Daniela, there are situations where you can have a breakdown of this temperateness, and it results in a very tricky domain behavior, which sort of has to do with Hardy spaces, but including singularities. So I'm afraid I can't give a very direct link here.
I see. And one other thing, which is maybe a bit even more naive than the previous one, but still it somehow bothers me for some time now. You see, when we think about the classical integrability, Liouville integrability for a Hamiltonian system, so it has the remarkable property that it's a global topological phenomenon. So locally, everything is integrable in classical mechanics because you have Darboux theorem. There always exist the right coordinates in which it is integrable. So integrability is a global phenomenon. So do we have anything like this, say, in the quantum field theory setting, any local triviality of the notion of integrability? I don't know local in which sense, but whatever.
Well, that's a tricky one. I mean, it is certainly true when you concentrate on scattering that this is also something global here, yeah? Because it talks about asymptotic properties. Yeah? So if you take factorizing S matrix as your definition of integrability, it captures global things in a way. Yeah? That is true. Locally, no, I'm afraid I don't know very much. I mean, what I would like to see is to somehow see these conservation laws more explicitly. Yeah?
Exactly.
I don't think that has been studied very much. What is going on here on the operator algebraic side is what's called the split property, yeah? When a certain two commuting algebras are in a tensor product situation. Yeah? So that's also what's behind the efficiency of this modular nuclearity condition. So that has to do with you somehow being able to implement global symmetries locally. Yeah? Right. So that has a somewhat similar flair, right? So when you have an inclusion of two regions, a small one and a bigger one that is split in this specific sense, that you could find operators in the big algebra implementing these on the small one. Yeah? So that has very much the same flavor. But I think it's not really much worked out, but sounds like an interesting thing to consider. Yeah?
Yeah, I would think if one tries to somehow model those conserved quantities or yeah, the symmetries through the automorphisms of local algebras and ask himself or herself the question whether or not these automorphisms extend to global automorphisms on a larger algebra, that somehow resembles already the Liouville kind of situation, if you think of automorphisms as being degrees of freedom.
Automorphisms as degrees of freedom, I'm not sure about. That would be new to me.
Yeah, because the dynamics is given by one-dimensional group of automorphisms, right? So if so you can think of a certain good subgroup of automorphisms as your kinda phase space. And different directions would give you different dynamics. If you have, say, n commuting dynamics, then it's kind of integrable, and which should be related to the fact whether or not you can extend that group of automorphisms from the local, smaller localized algebra to the larger one. If you can, then all degrees of freedom locally are actually global, so there are no internal free degrees of freedom, which is kind of non-particle creation. I mean,
yeah, I can only say you seem to have interesting plans, but I don't really know much about it, I'm afraid. Yeah,
I wouldn't.
To have a better understanding would be great. Absolutely.
Yeah, that's something I'm thinking of trying to work on. So and this seminar was a good occasion for me to kind of refresh my mind and to learn a couple of things of what exists and maybe.
Yeah, to put that on a very solid footing, these local, say, conserved quantities first of all, maybe some conserved currents or something like that. Yeah. That would be a big step. Yeah. On the other hand, I mean, if this would mean that you need to construct some explicit local operator, then my guess would be that it's almost bound to fail by complexity, like preservation of difficulty, essentially. But if you don't need them too explicit, that could be a way out. So in the split setting, so you then know existence of certain implementers, and you can typically not compute them explicitly. Yeah? But you can study their properties indirectly with this method. So if it's along these lines, I would be more optimistic.
Good. That's good to hear. So yeah, I've been talking a little bit too much. Maybe further questions from the audience, please.
Maybe I could ask a question. So the wedge locality itself could indicate that there can be some description of field theory where the fields are not dependent on a point, but on some space of the, right? So is there any formulation that somehow tries to deal with this?
I mean, there is a definition also abstract of what a wedge local field is, or some people look at what they call string local fields that depend on this is more on higher dimensions where they depend on a point and say some ray, space like ray going away from it off to infinity. So all that exists certainly, and models like that exist. So from my perspective, these are auxiliary quantities. You know? If you're really interested in the truly local fields or local observables, then these are convenient but auxiliary quantities. You know?
This is something similar to so-called Dirac string that is introduced to describe.
Yeah, so these, sorry, yeah, so these string local fields are, so that's different from what I talked about here, but they are inspired by something like that, yeah? Oh, let me think, what was that? Yeah, it had to do with choosing, it was inspired from QED and choosing some gauge depending on the direction. So not my work really. So there is work by Jens Mund, for instance, and together with Bert Schroer and Jakob Ingwersen, they have papers on string local fields. So for instance, if you look, that's one thing maybe I can mention. If you look into representations of the Poincare group, there's this infinite helicity representation, yeah? Which is long since known not to be compatible with truly point local quantum, Whiteman quantum fields. Yeah? That has been investigated in this setting of string local fields. Yeah, so there is a connection maybe, but the conclusion is there are no local observables attached to it. So opposite to what I talked about here, yeah. So there you can argue there's nothing truly local associated.
I think at least what I'm familiar with, there is a standard local Lagrangian, at least for free fields that carry this infinite spin representations.
Yeah, but there is no local field associated with it. I think the proof that there is no local Whiteman field is from the 70s or so. Yeah? So that's an old story, but it was then extended in various ways. In the end, the conclusion is that does not admit any local observables. So that is formulated.
Literatures, I guess. So it would be nice to understand the connection.
I can point you to the kinds of papers that I have in mind. Maybe you mean something slightly different, yeah? It was this infinite spin that is oftentimes, when you look at representations of Poincare group, just discarded.
I'm familiar with it, yeah. So the thing, so basically from the field theory perspective that I'm familiar with, that people looked, you can understand it as a collection of kind of all helicities together. So in this representation, it's kind of like infinite number of particles per point. So that's how we view, and you can write some sort of action for it.
It might well be that you can write an action for it, but that would be very different from writing a local quantum field. But yeah, it might be interesting to compare that. I can, if I somehow get your email address or so, I can send you the papers that I have in mind, and then maybe they fit into what you know or not. That I don't know.
I will write in the chat my email.
Okay, that's very good. Yeah, let's do that.
Thanks.
All right, further questions? So maybe I dare to ask one further one.
That's okay.
Yeah, so regarding the regularity definition for the S matrix you gave, that its analyticity extends to the boundary including. So do you think it is close to having any reasonable interpretation, or would you say it's just a technical sufficient condition?
That part, I think, has a reasonable interpretation too. Yeah? Mm-hmm. So that is because, well, let me go to this modular nuclearity condition. So there is this condition that this map here, I hope you can see my cursor at the moment, should be nuclear. And this is, you can phrase it as some kind of partition function being finite, a modular partition function. Yeah? It has its origins in previous work by Buchholz on thermodynamical properties of quantum field theories. And there was a different kind of nuclearity condition that involved the Hamiltonian rather than the modular operator. And that was designed in such a way that it implies that a quantum field theory has reasonable thermal behavior, so that it has KMS states, for example. No? Yeah, and the two nuclearity conditions are linked. Yeah, so there are implications one way or the other under certain additional assumptions. So if you break one of them, you could expect that thermal behavior is in trouble. Yeah? And how could you break this extension to the broader strip? Yeah, so if you have, so where was it here? How could you break that? Well, you could formulate an S matrix that has many poles outside the physical strip, but that come closer and closer to the physical strip and approach it. And they would be interpreted as metastable particles with longer and longer lifetimes, and infinitely many of those. And that would be a situation where you would expect the thermodynamical partition function to diverge. So here there is a reason to expect this not to work. There is no strict proof, yeah, but I would expect if such a field theory would exist, it must have pathological behavior. I should also mention it's not only about analytic, it's also about bounded. I mean, there are examples of S matrices that are even entire, but no longer bounded outside the physical strip. There is one, there's a simple exponential form that comes, can be seen as coming from some non-commutative spacetime. You would expect locality to fail. There is no proof in that setting, but we expect that there are very few or maybe no local observables whatsoever in that case. And then there's yet even other stuff where you can, well, there's in some sense you can talk about S matrix 0 also. That does not fit entirely into this framework, but can be put in this language, and that brings you close to models of free probability, what I'm currently looking at with Ricardo, who's also here. And there we have strong reason to believe that it is very non-local. So in other words, with no additional assumptions on S, you won't get through. So there must be certain additional requirements, I think. Yeah.
Well, yeah, the analyticity properties in the Fourier space, they are known to be related with thermal properties. So I was just thinking whether this condition that it extends exactly beyond the 0-1, so to speak, vertically.
I mean, I maybe should also mention there are situations also, namely when you consider bound states, as Jo and Daniela do, then you even have poles in the physical strip between 0 and pi. In that case, a few things do change. For instance, this basic commutator theorem, where is my basic commutator theorem? The one down here is no longer true because you pick up residues. So you need to modify these fields and add some additional terms, which are then also responsible for destroying this temperate behavior. So in that case, you still, I mean, many things are much more complicated and not as well known as in the case without bound states, but you would expect, looking at the form factor literature, there should be a reasonable quantum field theory out there with these properties. So I would not say that this is absolutely necessary. So there should be extensions which allow for it. But in some configurations, as the one I described with these poles approaching the boundary, I think if there is a field theory, it will be pathological, at least on the thermal level.
All right, thank you. Further questions from the audience, please?
We had lots of questions. I'm happy to take more, but maybe people are exhausted too.
So if there are no questions for the formal part, then we'll probably finish the formal part of the seminar with this, which basically means I stop recording.